Good morning, everyone. So we're going to be doing our last lecture today of material that's on the midterm. I was just getting the slides ready to upload for the midterm review we're going to do tomorrow. We've got the practice exam is posted on Canvas. If you look under Files, Practice Exams, there's an exam in there with questions. It's a real previous exam. And then at noon tomorrow, there's another PDF already set to auto-reveal in that folder that has all of the answers marked, and it also has explanations of each of the multiple choice answers, and it's got code written out for the coding problems. So tomorrow we're going to go through the slides and the written problems together, and then anything else that we have time for. So today we're going to talk about ideas for sorting. When we looked at quicksort, we tried to divide it says here file, we mean just whatever it is you want to sort. So we take what it is we want to sort and we divided it into two parts by partitioning. And we ended up with some elements, the partition value, and everything else. And the downside to a quicksort was that it didn't always split it evenly. So Mergesort, the idea of Mergesort is we're going to take two regions that are already sorted and combine them into one large ordered region. Now, a little bit of history. Mergesort was invented for tape drives, which you probably haven't seen except in pictures. And so you could have a file on tape drive that was larger than would fit in memory. I mean, you might have a 20 kilobyte tape drive and only have 2 kilobytes of main memory, which, seems like ridiculous numbers. But the same discrepancy in memory still applies today. You might buy a machine that has, say, 16 gigabytes of RAM or 32 gigabytes of RAM, yet you would still have a hard drive that's many, many times larger, like 1 or 2 terabytes. There are even 10 terabyte SSDs now. Just one second, I'm going to add, since Nigel's here, I'm going to add Nigel as a moderator for the channel. Okay, so if anybody gets out of line, he's in charge. All right, so these discrepancies in sizes still persist today. There are things that we might want to sort that don't fit in memory, and Mergesort was designed to work in this case. So we've got, for comparison here, just a basic outline of quicksort and Mergesort. So quicksort works by partitioning the array, trying to split it into the small region, and really, it does split it into the small region and the big region, and tries to hopefully make them close in size. And then we recursively call a quicksort on each half. The idea of Mergesort is that we are going to call Mergesort on the first half and Mergesort on the second half. And after it is done, the first half will be sorted and the second half will be sorted. So we'll get each half sorted and then we will merge them together. And this recursive approach will keep going. Now here we've outlined the top-down approach. So top-down approach means, how do we look at solving the problem? We look at it as, hey, here's a big thing to sort. Let's get the first half sorted and let's get the second half sorted. And then once I've finished that big picture, I can combine them into one sorted region. Now, no work actually gets done until the recursive calls happen. So we look at it from a top-down, but really, as the recursive calls go to half of the left half of the region, when we do that, that immediately makes a recursive call to the left half of the region. So, and of that region, which means it's the left quarter, and et cetera, et cetera. So we've got it here in a slide animated out to look at how we will break this down. So we've got here a sorting example with Mergesort. We've got 8 items, and we've got the value 1, and we've got another copy of the value 1. So we underlined it to make it obvious which one it is to begin with. So we start out by saying, I would like to merge sort the left half. So we make a recursive call to the left half. Now remember, the outline said recursive call on left half followed by recursive call on right half. Until the recursive call on the left half finishes, we can't make that call to the right half. So the animated slide here is actually laying out the order in which it happens. So then we've got this region of size 4. We say, well, I would like to recursively sort the left half. So now we've got 5 and 2. Let's recursively sort the left half. Now we're down to a region of size 1. We can use what we did in quicksort here. This is a base case. Once I reach a region of size 1 or size 0, it is sorted. There's nothing in this region of size 1 that is out of order. So now we've completed this recursive call to the left half. We can make a recursive call to the right half, and notice that that is sorted. Now remember, we were in the middle of a recursive call that had recursive call left half, recursive call right half. Once those are done, we can merge those two together into a sorted region of size 2. Now we've finished the recursive call. So this is all the recursive call that started out when we said, hey, I need to do that region, the first 2 elements there. So now the question is, where do we go next? And I know I'm 30 seconds ahead of you, so you think about it. Where are we going to go next? Has got to be to 4, 7. So we finished the left section of the 5, 2, 4, 7. Now we can do the right half. Mergesort doesn't know, and I'm putting it in air quotes if you could see me, Mergesort doesn't know that this region is sorted, so it makes a recursive call to the left half. That's a base case. Recursive call is done. Let's make a recursive call to the right half. Base case, that recursive call is done. And then we have a merge to do. We merge the 4, 7 together into a sorted region of size 2. Okay, so now I'll give a slight pause again. What happens next? So we've got these 2 recursive calls that have finished. Well, after a recursive call finishes, or after the set of recursive calls finishes, we have to merge these together into 2, 4, 5, 7. And we'll look at how to do the merging in a minute. All right, now we've finished with that region. What happens next? We've got to make another recursive call to the region containing 1, 3, 6, 1. So we make our recursive call to that region, and I've been sort of skipping this step. When it's not a base case, I haven't said anything. No, don't be sorry. That's why I want you to answer. So we've got this region of 1, 3, 6, 1, and there should be a check here. Are we at a base case? Okay, we're not at a base case, so we've merged sort the first half of this, 1, 3, and then we go to, well, this isn't a base case. Recursive call to the first half, that is a base case. Recursive call to the second half, that's a base case. We can now merge them together. Sometimes if you join late, you have to hit the play button. Someone will probably tell you that. So now that we've got 1 and 3, we can combine these 2 sorted regions by merging them. And then once we've got that one done, we have to go and finish sorting this. We've got to pick up where we left off. We're going to get to the complexity in a minute. So now we've got to recursively call to 6, 1, make a recursive call to 6, that's a base case, recursive call to 1, that's a base case, and then we merge those together into a sorted region. Now the 1, 3, and 1, 6, we've finished 2 recursive calls. Those can be merged together into a sorted region of size 4. And once that is done, again, we have finished a recursive call. We go back to where we left off, which was, hey, I need to recursive call this right half. Well, now I've completed the left half of the original, the right half of the original. We can now merge them together into 1, 1, 2, 3, 4, 5, 6, 7. Now, one of the things that is in here but not really obvious is what happens, let's back up one slide, or one set of animation, when we want to do this merging portion here. If I think of this as, hey, this was all one array to begin with, so I've got the first half sorted, I've got the second half sorted, let's merge them together. So I say, well, I know this is the beginning of a sorted region and this is the beginning of a sorted region. Which one should come first? Oh, that one. Well, let's swap them. Oh, okay, let's swap them. So I put the 1, remember, this is really just one big sorted region. So right now, so I've got 2, 4, 5, 7, 1, 1, 3, 6. And I say, okay, let's swap the 1 and the 2. Okay, let's do that. 1 goes here, 2 goes here. Now I know this one's sorted, but I still haven't sorted this one. I'm still right here. But wait a minute, there's a 1 behind it. By doing a swap, I've made these out of order. So the merging isn't quite as easy as it looks when we've got an array to do the merging. So we're going to actually need some extra memory to help us with this merging step. We can't just swap values because we might produce something that's no longer sorted. Okay, so we get that sorted. So before we get to the how to do the merge sort and the merging and the base cases, etc., real code, let's look at our some concepts about merge sort. So, like I said before, the merge sort was designed to be an external sort, and you would typically run it with multiple tape drives. You would take stuff from one tape drive and copy it to another, and once that one was sorted, and you'd have to sort into 2 different tapes, and then you'd merge them back into a third tape. A bit painful. A lot easier to write when we're actually going to write it with arrays. We'd like to, if we could, we would like to sort in place with no extra memory. That would be our goal. But sometimes it doesn't fit in memory. So we might say, well, I'd like to put the items representatives, the key or the index. I'd like to put the indexes in memory, and let's sort the indices, and then I will say where it is on disk in what would the sorted order look like. That, hey, the first item is at this location, second item is at that location, and I could sort the indices. Well, we still might not have enough room for that. So we might have a situation where we have to keep the data in an external storage medium, and we can only keep a small part of it in memory at a time. We'll get back to that issue, Kevin. We're going to come and talk about that again later on. So we're going to need additional memory here, and part of that is for the merging step. So we're going to look at merging. Before we look at merging, we need to understand notation in C++. So we're going to use the ternary operator, the question mark colon operator. The ternary operator is something that's really useful in C++. It is called the ternary operator. Let me spell that out. It's called the ternary operator because it has 3 operands. So a unary operator like plus plus has one operand. A binary operator like %sign has two operands. The modulus operator, the equals is a binary operator, has two operands, and there is one. This is called the ternary operator because it's the only one. So what the ternary operator does is it has three portions. It's got this first part, I'm going to erase that. It's got the first part here is an expression to test for true or false. So this is evaluated, is it true or false? This section here is the result if true, and this region is the result if false, if the first expression is true or false. So this is saying C sub k gets assigned something, gets assigned the result of the ternary operator. What does the ternary operator do? It says, well, let's test. Is A sub I less than or equal to B sub j? If that is true, then A sub I goes into C sub k, and I plus plus happens. Else, we can think of this as an if-else, else B sub j gets copied into C sub k, and then j gets incremented. And the increment happens last because it is a post-increment. It's j plus plus means we look at the current j, then after we've copied B sub j, then we increment j. This one line of code is equivalent to our 1, 2, 3, 4, 5, 6 lines of code plus curly braces at the bottom. So equivalent version at the bottom here says if A sub I is less than or equal to B sub j, take A sub I and assign it to C sub k, and then increment I. Take what's in B else, take what's in B sub j and assign it to C sub k, and then increment j. Now this version, because the plus plus happens all on one line, we could use pre-increment instead of post here, but I wanted it to be consistent. So this is really the order of operations that happens in the ternary operator. And the other important thing is that even though the ternary expression contains both I plus plus and j plus plus in one line, only one of them gets evaluated. If the first expression is true, then this is evaluated, and the second false, or the false expression is never even looked at. So it's equivalent to the bottom in that if the first expression is true, I gets incremented. If the first expression is false, j gets incremented. Now, is there a reason to use the ternary operator? Do we need it? There's a very few places where it's needed. It doesn't, that's what I was going to get to next, is Samaya's question is, this doesn't affect our memory, it doesn't affect runtime. Ternary operator is mostly used for readability, in that once you get used to reading it, it can make code easier to read by making it shorter. Now, sometimes making things shorter makes them harder to read. So there's actually a programming contest every year called the national, or actually international, it's called the Obfuscated C++ Programming Contest. And obfuscated is a fancy way of saying hidden. So what the idea of the Obfuscated Programming Contest is to make a program whose purpose is hidden from a human being reading your code. The whole idea is to write the most unreadable program possible in whatever that year's limit of characters is. So there's a limit. So you can't write, like 100 or 1,000 line program. You're allowed, like, say, 300 characters. And you have to write a very cryptic program in 300 characters. To do that, all one-line variables, and the more of them there are, the harder it is to read. You can't afford to press enter between lines of code, so it is typically like include statement, and a hugely long line of code after that, or really int main with one line of code inside of it and curly braces all on one line. So it's usually like a 3-4 line program, because you need one or two includes just to get like IO stream or something like that, and then like 250, 300 characters of incomprehensible stuff. And one of the ways to make it incomprehensible is to use ternary operators. And I said plural for a reason. Ternary operators, where each part of this, like this is a ternary operator, that's a ternary operator, this is a ternary operator, and so is that. And we pack them inside of each other, wrap a loop around it or 3 loops around it, and you get bonus points if not only is it unpredictable, but it does something really cool. Like there was one year that in like 300 characters or something, they drew a Christmas tree, and then the Christmas tree started spinning. And it is yeah, obviously you would write it in multiple lines of code, and then you'd pack it down until it's unreadable. So the downside of the ternary operator is that it can make code harder to read. Especially we don't want to nest them inside of each other. But in some places it can make things shorter and easier to read if you use them sparingly and you get a little bit used to seeing them. So we did this now for 2 reasons. 1, to remind you of the existence of the ternary operator, and 2, because we needed to fit the code on one slide, we needed the ternary version of this. Okay, so here's our merging process. So what this says is if you give me an array C, C is where I'm going to put the result. Then you give me array A and tell me how big it is, array B and tell me how big it is, and we make the assumption that that this array C must be big enough. It's got to be at least size A plus size B. So it's got to be that big. It could be bigger, but it's got to be at least that big. So let's look at the code here to produce this merging. So it says, hey, I'm going to run a for loop, and we're using a trick of the for loop here. We've got 3 different variables created and initialized all at once. You are allowed to do that. The one thing about them is they must all be the same type. So you couldn't create like an integer and a string, but you can create multiple integers. And you can assign each of them a value or different values to each of them. So here we've got I is equal to 0. I is going to be our index into the array A. I is going to be our subscript into that. When we've got the array B sub J, J is going to be our subscript into there, and C is going to be subscripted by K. K is going to be our index into the sorted region. So we've got an index I into A, J is our index into B, and K is our index into C. All right, so we start them all at 0. We're going to keep going as long as K is less than the total size. And every time through the loop, we are going to increment K. But sometimes I gets incremented, sometimes J gets incremented. Didn't realize that wasn't answered yet, Kevin. I don't know JavaScript as well as I should. I know there's no ternary operator in, I don't think, gosh, I've done Java so seldom lately. It's not unique to C++, but not a lot of languages have it. Okay, so let's look through the code here. So we say, if I is equal to the size of A, then what goes into C must come from region B. What this is saying is, have we reached the end of A? If we've reached the end of A, then the remaining values must be coming out of B. Else, if we've reached the end of B, and remember here, our index here is inclusive exclusive. If I is equal to the size of the region, so if let's say size A was 4, we start out I at 0, 0, 1, 2, and 3 are valid, As soon as it becomes equal to the size, it's an invalid subscript. Okay, so we've got, if it's the end of A, it must come from B. If we're at the end of B, it must come from A. Else, if we are not at the end of A or B, then we've got the ternary expression that says basically take the one that's less than or equal to, if A sub I is less than or equal to B sub j, take it from A, else take it from B. So we get the value from A if it's less than or equal to the value from B, else we get the value from B. So we're going to take basically the smallest remaining element has to go into the output, and then we move forward in that region. The complexity of this we can see, k gets incremented every time, and k goes size of A plus size of B. So this big theta is always this complexity. It's never faster, never slower, always takes this amount of time, but it does make the assumption to do this merging, A and B must be sorted ranges before we can merge them together into a bigger sorted range. Now we could potentially rewrite this into working with other data structures. So like I said before, Mergesort was really made to merge tape drives. Tape drives had sequential access. You read as the tape goes flying past the read head, you read sequential locations. We could modify this code to work with linked lists. Now we've got an illustrated example here with a couple of things happening. One is we've got two different sized regions, and two, we're going to track our indices all the way through. So we've got up at the upper right, we've got the size of A and B listed, so we've got slightly unequal sizes. This is what would happen if we had 7 elements instead of 8. We don't have an even split all the time. In that example, arrays are always passed by reference because it's the default, because remember, passing an array is like passing a pointer. Okay, so in this example, we got 2 different sizes, and what we're going to do, let's go through this animated slide. So it says, when k is equal to 0, and we know that I and j started out at 0, it says, is A sub I less than or equal to B sub j? And then we've got all of these expressions in here to show you what they are. So I happens to be equal to 0. So when I say A sub I really mean the capital A. And when I look at B sub j and j happens to be equal to 0, then I'm talking about the letter capital B. Is A less than or equal to B? Yes, it is. Therefore, the A is the one that ends up in the output, and I gets incremented. So I gets incremented because we took from container lowercase a. Okay, so we move on. The for loop increments k. So now when k is equal to 1, we compare A sub 1 to B sub 0. Is D less than or equal to B? No, it's not. So the capital B has to go to the output region. And if the capital B, which came from lowercase b, goes to the output, then J must be incremented. All right, we move along. K gets incremented to 2. We compare A sub I to B sub j, and we've got D. Is D less than or equal to D? Yes, it is. So D goes to the output. And we've got slightly different colors here. I don't know if we've run into this semester or not. Word about me, I am colorblind. So the first one, region A, looks like the letters are in gray. Region B, they are a different color. I am afraid to commit to a color there for the capital B, capital D, capital F. I'll say purple. You can play along. Or you can correct me. I don't care. I really don't. You should have seen me in electronics lab as an undergrad when resistors were color-coded. Had my roommate help me put them in little tiny baggies all labeled with what their resistance was. Okay, so because we looked at the one from region A, the gray D, because it's less than or equal to the purple D, the gray one goes to the output, and I gets incremented. When K becomes 3, we look at A sub 2 versus B sub 1. Is G less than or equal to D? No. So the D from region B goes to the output. So the capital purple D goes to the output, and J gets incremented because we took from region B. Okay, K gets incremented. Is G less than or equal to F? No. So the F goes to the output, and we increment J. Now when we increment J up to 3, J is saying, hey, this is where I am. We have now reached the point where we are off the end of container B. So once we're off the end of container B, because we've got that test, then what comes from region A must go to the output. And we just keep looping through until we finish with everything in region A, and then we're done. This is not meant to be assignments. This is not meant to be code. This is meant to be how you look at the what's happening. So if we had written code this way, we would be assigning values to I. So this wasn't meant to be a coding representation. It's made to be keeping track of where we are as the code progresses. So when we say J equals 2 here, we're saying that is what it gets set equal to. Really what happened was a plus plus. So we've gone through this animation, and it's similar, yes, except when we did the union of two sets, we did it all with iterators. So it is very similar to set union, except for one thing. In set union, when we had 2 copies of D, only one of them got into the output. But now, since we are doing the merge, the duplicates get into the output. So slightly different, Jingyi. So slightly different because we want the duplicates to make it into the output. Because there were 2 Ds in the original unsorted, there must be 2 copies of D in the final sorted. Now, going back to a question someone had a while ago, was it an accident that the ones stayed stable? Well, that's a good question. Let's look at this one. Was it a lucky accident again that the D from region A got there first? Was it an accident, or was it something we planned? And if we planned it, what part of it is making that gray D get there before the purple one? So think about that for a few seconds and type in an answer when you come up with one. And little pauses like that give me a chance to get a sip of water while I'm teaching. So once might be a coincidence, twice is, or once might be happy circumstance, 2 might be a coincidence. But it turns out we really did plan it this way, and we didn't just make an example that would accidentally put the left D first. No, Kevin, that's not quite it, because both regions must be sorted first. It's the, Evan's right, it's the less than or equal to, and it's specifically this one here. Because of the less than or equal to, the left one gets into the output first. The order of the recursive calls wasn't important. We tend to do it left followed by right, but it's not critical to getting the stability. So the sizes don't matter. The which region gets sorted first doesn't matter in terms of getting stability as our result. Now, if we had regions of like size, if A was size 3 and B was size 4, it would still be fine. What we don't want to have is we don't want to have like a region of size 10 and a region of size 1. That would not be splitting it evenly. So they've got to be either the same size or off by 1. And if we look at how the code gets written in a little bit, we're going to tend to see that the integer division is going to tend to make the first one bigger by 1 if the sizes are different. So just the way that we calculate beginning and end of each region is going to tend to put the big one first, but it's not critical. They could be sorted in any order. They could be, the slightly bigger one could be second. What's critical is the less than or equal to there. Okay, so here's our code for Mergesort, along with a call to merge. Now, wait, let's go back one slide. I got to go back multiple slides. This was called merge AB. It's slightly different from the merge that we're going to use in a minute. We needed to write a version that worked first and to see how we had to have those separate regions before we get to the slightly more complicated one. So in this one, it's called merge in line 7, slightly different function, which we're going to look at soon. It's going to be very, very similar. Okay, so here it says, I would like to merge array A using Mergesort, and I'm going to tell you the left inclusive and right exclusive indices. So to begin with, left in the very first call, left would be 0, right would be the size of that array. Then, because we're going to have recursive calls, first we've got to have a base case. So the base case says basically if there's less than 2 items, then it's already sorted. So if it's size 0 or size 1, we can return. This region is done. Okay, otherwise, if we didn't return, we don't need an else here, because if the function is done, it's done. If it didn't do a return, then we pick up at line 4. So we figure out where the midpoint is. So the midpoint is left plus right minus left divided by 2. This is important. I mentioned this previously. If left and right were kind of large, we could have integer overflow with still a valid size array. We don't want that to happen. This is safer. And if we were using iterators or pointers, this would work with them. If left and right were pointers or iterators, we can take an iterator minus an iterator gives us an integer. Integer divided by 2 is still an integer. Iterator or a pointer plus an integer is another pointer. So this syntax is both safer and more versatile. Okay, so we figure out what is the midpoint. Then we merge sort from left to mid, and notice the inclusive exclusive in this line. So we go from left up to but not including the middle. Then we make a recursive call from the middle inclusive up to but not including the right. So for example, if we came into this slide with, let's say, like our original example, left was 0 and right was 8 because the original array was size 8. We would say, okay, right minus left is 8, 8 divided by 2 is 4, left plus 4 is the middle, so we would go from 0 to 4 exclusive, and we would go from 4 inclusive to 8 exclusive, and we would have 2 regions of size 4. What if, let's just change it slightly, what if the right started out as 7? Then left plus right minus left would be 7. 7 divided by 2 is 3. Oh, I guess I'm off on that. I guess my example is backwards. Okay, so right minus left would be 7. 7 divided by 2, integer division is 3. We would go from 0 to 3, and we would go from 3 to 7. So it actually, the larger region would be second, my bad. So we merge sort each half, we make our 2 recursive calls, and then we make our call to merge. Now we need a slightly different version of merge because all I have is one array. I have one array. I don't have array A and array B and array C as a different array to put them in. all I've got is array A, and I'm telling merge where the regions begin and end. I'm saying left, mid, and right are telling you where the regions of A are. And so merge has to do its job within that array. Now, this is what's called a combine and conquer. This is an Englishism that is really slightly different from reality. So we've looked at items, we talked about quicksort being divide and conquer. This one is called combine and conquer. Really, a slightly better name would be conquer and combine, because that's what happens last, is the combining step, the merging step. So really, we conquer the first two regions by sorting them recursively, and then we combine the results into one sorted region. Now, let's skip down to the bottom question. Is it safe to use recursion here? We have two recursive calls at lines 5 and 6. Are they tail recursive? No, they can't be tail recursive because line 7 must happen after both recursive calls have happened. So neither of our calls is tail recursive. So this thing is not tail recursive. So then to answer the question, is it safe? What about the recursion depth? Could we have so big of a recursion depth that we couldn't fit it within a stack, or the allowed stack memory? Well, what about if we start out with a big array? Let's say we had a size 1,000,000. Because we know in line 4 we have found the middle, or just one off of the middle. Because we have found the middle, we know that we have split it into two either equal regions or different only by 1. So if I divide it in half each time, then the depth of the recursion can't be more than approximately log n. So this one can never have a recursion depth of more than log n. If we had 1,000,000 elements, log n is 20. If we had 1,000,000,000 elements, log n is 30. So even if we had 1,000,000,000 elements, if we had basically like if it was integers, it'd be 4 gigabytes. If I had a 4 gigabyte array of integers, I could still do it in a recursion depth of 30. I'd be more worried about can I have an array of size 1,000,000,000 than I would be a recursion depth of 30. So this is perfectly safe recursion because it always divides it in half or as close to half as possible when we get an odd size. Now, this proceeds, like I said, we keep making recursive calls until we get to base cases, and we've already stepped through the animation, the animated slide and the animation of how the small regions get merged into larger ones, and larger regions get merged together into still larger ones. Now, let's look at a modified merge. So this modified merge has to understand that it's going to do its work. It came with one source region, array A. It has to assort basically A sub left to mid is one region, and then A sub mid to right is the other region. So they are both regions of the same array. They must be merged into somewhere, and that's where our vector comes into play. So with the vector here, I created the vector with size n. So I figured out what is n. N is the size of the total size of the array A coming in, right minus left. Once I know that size, I can create an array of that size, and it's all initialized to default values, but it doesn't matter because I'm not going to look at them until we're overwriting values. So then the rest of this code is almost the same except for two things. One is not everyone starts at 0. So K starts out at 0. K is our index into C, but I starts out at left. I is our index into the first portion. J is our index into the second portion. So that's why A starts out equal to left, and j starts out equal to mid. So that's one difference, is our starting points. The other difference is there's no A and B anymore. It's all A. It all comes from region A. So everything we compare is in array A. It's just a different section of array A. We either look at it in the I-indexed region of A, or we look at it in the J-indexed region of A. So other than that, we just take what we've got in the original array A, and we store the values into vector C. Did we have to use a vector here? No. We could have used dynamic memory. It would have added one line because I would have had to do a delete when I was done. So saved one line of code by doing the vector, and it's slightly safer in that if I had forgotten to do the delete, I'd leak memory. But here, with the vector, when the function ends, vector destructor runs, and it cleans up the dynamic memory for me. So we made it a little shorter and a little bit safer. So our loop is the same basic loop except for the starting points and the fact that it's A all the way through A sub I and A sub J. And then when we're all done, we're going to use standard copy. This is part of the STL. We're going to use standard copy to copy from C back into A. So we've got to copy the entire vector contents of C from beginning to end, and we've got to put it back in A. But if I just say A is a pointer to the beginning of A. I've got to say the address of A sub left. And if you don't like it, this is a place where it is safe to add parentheses. It's not necessary. Subscript has higher precedence than address operator, but I think it's sometimes a little bit easier to read if you see that, yes, definitely the ampersand happens last. We can't just swap here because I've got an array and a vector. I could swap two vectors. So if I modified this to take vector A passed by reference, then we could conceivably do a swap when we're done. So this one is better because we can do it with one array and we just temporarily create the region to copy into. And we'll get back to the memory in a minute because we've got to come back to that issue. So we're going to come back to that now that we've seen how this really works with allocating memory each time. So we'll come back to that. After we're happy with this slide, we'll go back and talk about memory. Now, so A sub left, why A sub left instead of A? Well, because at certain points in the sort, we're not talking about the beginning of the array. So let's go back to our animated slide and look at, so here's our animated slide that we had. Now, at one point, like at the beginning, like when I'm doing this region, left is 0. Left is 0 and right is 4. But when I'm working on this region here, left is 4 and right is 6. So that's why it's the address of A sub left. Okay, so going back to answer questions. So Sean, we wrote a merge that only worked with two separate arrays. Then we wrote a better one that can copy from two regions of the same array and use a temporary storage to where to merge to and then put it back where we got it from. So we started with two separate arrays, then we moved to two separate regions of the same array, but we still need a vector, a temporary storage region to actually merge into. So we've improved it somewhat. Now this slide also lets us look at memory usage. So notice that as the recursion depth goes down, we need smaller temporary arrays. So here was my original call. So this is at a recursion depth. Let's label recursion depths. So this is 1 level deep in calls. This is 2 levels deep. This is 3 levels deep. This is 4 levels deep is the base cases. Then as we return, this is 3 levels deep, 2 levels deep, 1 level deep. So when we are at 1 level deep, at a depth of 1, we need a region of size n to do the merging. When we're at a depth of 2, we need a region of size n over 2, which gets used for this half. Then that gets destroyed. Then we make a recursive, then our recursive call in the other one makes an n over 2, which is then destroyed. So we never need more than n over 2 at a time, because only one merge is happening at a time. Merge happens and then it ends. When we're at a depth of 3, we need regions of size n over 4, but we only need one vector at a time. Then it gets destroyed. Then a different region gets merged with size n over 4. Then that vector gets destroyed. So as our stack space grows, our vector size shrinks. So we never have to worry about our recursion depth being so high that we overflow the stack. But what's our maximum memory usage now? Our maximum memory usage is n. At the topmost level, we need n. When we're at a depth of 2, so it's n, really it's n plus 1. I needed one stack frame and I needed n, so it's n plus 1, which is O of n. So my memory is really n plus 1, the stack frame plus the temporary vector. When I'm at a depth of 2, I need 2 plus n over 2, which is still O of n. Here I need 3 plus n over 4, still O of n. So now O of n is my maximum memory needed. So that's my maximum memory I'll ever need, is at the topmost level. Along the way, recursion depth happens and stack frames go on the call stack, but each recursive call uses less memory to make the merging happen. So we really have an upper limit of O of n on our memory usage. Now let me go back to, I got to find where we were. Okay, so that was our modified merge. So remember, copy has 3 parameters. It's got the from as an inclusive left end, our from as a exclusive right end, and our destination as an inclusive starting point, and the assumption is that there's room for it. So if I started out with an array of size 4, an array of size 8 here. If I started out with an array of size 8 and I separated it into 2 regions of size 4, when I do the merge, I put it back into the original array of size 8. So we're safe on our array size there. The destination is the right size. Now, it says here, it's fast. It's O of n log n. Well, wait a minute. That's pretty hand-wavy. Let's look at why. Okay, so let's go back. We need to go to this slide, and let's erase all these markings on it. Let's talk about time complexity here. So we already did memory complexity. Let's talk time. So we've got a base case. So actually we have 2 base cases. T of 0 is equal to C0. T of 1 is equal to C0. If I get down to a region of size 0 or a region of size 1, it takes a constant amount of work to realize, to make the recursive call, realize it's a base case, and return. So we've got 2 base cases. If we're not in a base case, we're at T of n. So T of n is equal to, well, all this stuff. Either it's a base case or it's, well, let's figure it out. I've got 2 recursive calls. Each of them is size n over 2. And the integer division will take care of it. Now, they could be off by 1. I could have a region of size n over 2 floor and a region of size n over 2 ceiling. If n is even, they're both 4. If n is odd, one is 3, one's 4. But that's a little too complicated. Let's just say n over 2. Kevin, the original memory is not included. We're talking about additional memory that was required by Mergesort. So you gave me the array of size n, that's your memory. Mergesort, I'm talking about how much memory did Mergesort, how much memory did I need? So I'm counting my memory, not your original memory. We're counting the extra memory required for the sorting. Sorry, I didn't make that clear. I should have. Okay, so there's our recurrence relationship. So I've got t of n is equal to 2t of n over 2 when n is greater than or equal to 2. And really, it should be plus c1. We should have, there's a constant amount of memory of time there for, like, hey, it takes me a constant amount of time to calculate the middle. It takes me a constant amount of time to make a call. Oh, wait a minute. We've got to include one other thing here. It's not just plus C1. It's plus n plus C1. Why n? Because after the recursive calls, we've got to merge them. We've got to do the merging, which we already said, the merging is big theta of n. And there's some constant factor there for the figuring out where the middle is. So when we counted the extra stack frames, remember, we never had more than, let's go back there. I didn't realize there'd be so many questions. Remember, here we have n plus 1 is what's required at that depth. At this depth, what's required is 2 plus n over 2. But when that recursive call is done, we give back this memory, we give back that memory. And we're back to the top level where we've only got one stack frame and we've got the n plus 1. Well, so even if it was that, that's still O of n. But it's not actually required all along the way. And Oliver, didn't notice you were here until now. I'll add Oliver as a moderator. So that's absolutely true. O of n is O of n plus log n is O of n, but it actually isn't all required at the same time. When I have the recursion depth, let me erase a little bit here. So let's go through this. So I'm at a recursion depth of 1. So right here I've got one stack frame. Then I add a second stack frame. So I had one stack frame, now I have 2 stack frames. Now I have 3 stack frames, and I need a region of size n over 4. But then I get rid of this. So I'm at log n plus n over 4, which is never any bigger than O of n. But then also, when this gets destroyed and I go back to a recursion depth of 2, I don't have any of that memory anymore. I'm back at a recursion depth of 2. I have 2 stack frames. I have an n over 2, which gets used and then destroyed, and I'm back to 2. So yeah, it's basically the O of n is the big term here. It never gets worse than that. Because when I'm at n over 2 plus 2, n over 2 plus 2, or n over 4 plus 3, is still less than O of n. Okay, let's go back to where we were again. Okay, so whoops, wrong side, sorry. Here we go, so our recurrence relationship. So we're trying to do our recurrence relationship. Well, now we've got a recurrence relationship that we can put into the master theorem. So we've got A is equal to 2, that's the 2 out front. B is equal to 2, that's our divided by. C is equal to 1. Oh no, it's I want to make sure everybody's got it. And I'm sorry, I'm delayed by 30 seconds or we would have stayed there. Okay, and our C is equal to the exponent there is 1. So now we want to know is how is A related to B to the C power? Well, we've got 2 is equal to 2 to the first power. That means we're in case 2. We go back to our master theorem, and spoiler alert for slides next time. Even though you're allowed to use your electronic PDFs, etc. for the exam, having a cheat sheet would still be good. Having a sheet of notes in front of you with things that you know you're going to need, like the master theorem, would make the exam go a little smoother because you don't have to go, ooh, that's in lecture 3. I think it's around slide 17. Oh, wait, no, that's too far. So it'd be a good thing to write these down like the master theorem and have them ready. So we're in case 2 of the master theorem, plug it in, big theta of n log n. So the time complexity for merge sort is big theta of n log n. Always takes that much time. Never takes more, never takes less. The constants are, like this would be C0, this would be C1. So we've got our base case time and our recursive case time. So we've got, so let's go back to the slide after this. So it's n log n. Really, it should say here big theta. Big theta of n log n. It always takes that amount of time. It's stable if a stable merge is used. So as long as the merge step is stable, then we have a stable merge sort. And stable merge depends on that, less than or equal to. So is A sub I less than or equal to A sub j? As long as that's less than or equal to, we should be good on our stability. Actually, the STL has standard stable sort. Standard stable sort uses a merge sort. Now, normally, like we said, normally the merge sort is implemented to access data sequentially. It doesn't require random access. We wrote it so that it does. But you could rewrite this to work with linked lists. You could rewrite this to work with files on disk. And I had a class, when I was an undergrad, we had a class in disk-based data structures. And one of the things we wrote, one of the first things we wrote was a disk-based merge sort, where we were only allowed, the only things we were allowed to keep in memory were the things that we were comparing or swapping. Basically, we were allowed to keep one value from each region in memory at a time. Everything else had to stay on disk. So we can do this with linked lists. We can do it with a disk drive, tape drive, whatever external storage we've got, we can do it. And it turns out merge sort actually works pretty well in memory also. It does great use of the cache, which is important to having a good sort. Now, disadvantage is, because it's big theta of n log n, it always does this complexity of n log n. We'll always have n log n comparisons. The merge sort is insensitive to input. It doesn't matter if it's already sorted or not. It's going to take n log n time to sort because it has no idea that it's already sorted. Now, it's going to require that O of n additional memory. Quicksort is in place, but quicksort needs the extra stack space. So quicksort has the extra stack space, but it is in place. Merge sort is not considered in place because we take and we merge into that separate region, and then we copy that separate region back over the top of our input. So merge sort needs this extra memory for that copying. And it also takes this extra data movement is, what the reason we listed this is extra time. That copying to and from does more work than quicksort. Where quicksort rearranges one container, this one rearranges into a separate container and then copies back to the original. And that takes a little bit of extra time. Usually quicksort does better on average. If quicksort starts making regions of small sizes instead of close to half, well then merge sort would do better if quicksort's partitioning is going poorly. So it typically does better than quicksort on average, but we could always, if I knew your quicksort algorithm, I could always design data that would make you do terrible with quicksort. No, not necessarily, Eugene. Look at other sorts, like is bubble sort stable? Is insertion sort stable? These are good things to know and maybe add to that cheat sheet before the exam. That's a good question. I keep forgetting to tell you guys that. The project one, I goofed. I forgot to set aside our hidden test cases. You were actually running with our hidden test cases from the beginning. So we don't have hidden test cases. So what I'm going to do is I'm going to rerun the project one grading just so that people who were slow because there were multiple people running on the server will get a better chance at getting rid of some blue because there were multiple people submitting at that time. So your scores for project one should not go down. But yeah, I've been avoiding it now because I didn't want to do it while project 2 was going. So I'm going to run the final grading for 1 and 2 after the midterm as project 3 is starting. And so I'll get that done soon. Okay, sorry for the digression there, but it was a good question. And an important one to answer that I keep forgetting. I keep answering individual people in office hours, but I keep forgetting to say it at lecture. Okay, so the top-down merge sort has that extra memory for merging. Now there is in place merge exists, but it has a disadvantage. In place merge, the code is so complicated that its constant factor is worse than our not in place merge. So the in-place merge exists, but it's so complicated that the constant factor, it's O of n, but it's O of a large constant times n, and this big constant makes it slower than our vector version. So the in-place merge does exist. In fact, it is implemented in the STL. You can look at the fact that it exists. I do not recommend looking at the code. It's one of the other things besides DEC that is heinous code to look at. Even not in the STL, just like a paper about in-place merge is just hideous to try to follow because of the reordering issue. Okay, so when we talk about merge sort, we're going to ignore that exists. We're going to talk about our version that does require the big theta of n additional memory, because it's not only is it all that we can write at the moment, it's more efficient in general, and it's what is used by standard sort, stable sort. The STL stable sort does not use in-place merge because it's too slow. It uses the not in-place merge with extra memory. Now, we did this, and I forgot to mention this, we've been talking about top-down this whole time. When we wrote the code over here, this is our top-down approach. This is going from bigger to smaller, saying, hey, If I've got a big array, I can split it into two smaller arrays. If I've got a smaller array, I can split that into smaller arrays. And then base cases sort of build up into the bigger solution. But the approach of the code is top-down. Now over here, we have the code for a bottom-up version. This one says, hey, now that I know that it's really all one array, I could look at it as if it is regions of size 1 and 2 and 4, etc. So that's what the code here does. Now, we don't want to dig too deeply into the details. Let's look at an example of it, and then we'll come back to it. Okay, so here's our array, and we're going to look at the code and the example together. So it says at the beginning, we start out with size 1. What that means is basically, I have regions of size 1 that must be combined into bigger regions, which will obviously, they'll be size 2. So we've got size equals 1 is how big is the regions we are going to merge, and then our loop here is basically how many regions, how many merges need to happen. So given that I have regions of size 1, how many merges do I have to do to get them merged together? So the way the bottom-up merge works is it says, hey, let's go and merge that first regions of size 1 into a region of size 2. So it runs 4 merges the first time through. So this is basically, this was one time through the outer loop. One time through the outer loop, the inner loop, so this ran one time so far. This has run 4 times, and we did 4 merges of regions of size 1 merging into regions of size 2. Then, when size becomes 2, so when size becomes 2, there are number of merges. It has to do 2 merges of regions of size 2 to get regions of size 4. Then when size becomes 4, so then size becomes, let's change colors again. So now when it has a size of 4, I have to do 1 merge on regions of size 4 to get a region of size 8. So that's how the code works, and that's the basic idea. Am I going to ask you questions about this code on the exam? No. But I expect you to know what the basic idea of top-down means. We start with big things and we go towards base cases. I expect you to know what bottom-up means. We start with the small cases and build the small ones directly into larger ones. Everything else in here is a little bit cryptic in how the size, okay, so the size doubles every time. That's pretty easy to understand. How does I go up? So I is controlling basically, I isn't really a how many times we will merge. I is an index into where should we merge. So I is basically an index into the first part of the first index of the region that needs to be merged. So then the last part here in the merge step, there's I is the beginning, I plus size, so that's an inclusive exclusive, and then that's the middle, and then the last one is where this is the right hand end. So this is I is the left, this is the mid, this is the right. So I was the left square bracket, I plus size is mid, and this is the exclusive right, and this thing is, yep, so that's what I was going to get to, Jacob, is that's what this min of I plus 2 times size comma right is it takes care of the odd sizes. So if we had a region of size 3, this expression takes care of that odd-sized region. So the code is a bit complicated here. It works. I've tested it extensively, but I don't expect you to know why exactly it's min of I plus 2 times size and right, etc. That's basically, like I said, that's basically there to deal with Jacob's question of regions that aren't exactly powers of 2. So if we had 7, we would have split it into 3 and 4. The size 3 would have been split into regions of size 2 and 1, and that thing takes care of it. And in this one, the odd region will actually always be at the end. So here it would be, because of how this one works, it would be actually 4 and 3. So if we get rid of one of these, get rid of all my markings here, if we got rid of this one, then we would have a region of size 2, 2, 2, and a region of size 1. Then those would be merged into regions of size 4 and size 3. And those would be merged into a region of size 7. And so the odd region is always the last one in this one. Okay, so here's a question for you now. Suppose I tell you I've got a file, it's got 100 million elements. How do you find the most frequent element? Well, one way would be we could do merge sort on the external data. With 100 million items, we can't make an array that big, so we could do merge sort on disk, and then we could find the biggest consecutive region of like 3, 3, 3, 3, 4, 4, 5, 6, 6. So we would sort it. Then once we find that it's sorted, we can find the biggest consecutive region. Now, if I told you that the most common element, if I had more data, like the most common element occurs greater than half the time, we could go back to Moore's, whoops, that's too many O's. We could go back to Moore's voting algorithm. Whoops, I forgot the E. If I told you it occurs greater than n over k of the time, then we could go to the Misra-Gries algorithm. But without that knowledge, we would have to go back to merge sort on disk, which is O of n log n, really big theta. It's big theta of n log n time. Because it's on disk, it's going to be slow. But if there's a majority element, then we could use a better algorithm that would be faster. These are O of n. These are both O of n in time, average case time, and the memory is dependent. This is O of n time, O of 1 memory. So this is time and memory. This one is slightly bigger memory requirements, O of k on memory. But k should still fit in memory. And it's O of n log k in time. So if it was a strict majority greater than half, that's where, yep, and that's where, yes, hash tables. That's how Misra-Gries works. So if you know what hash tables are, that's how the Misra-Gries algorithm works. For Moore's voting algorithm, we don't need it. We just need to count, we just need to keep the count of the most major element so far. Okay, so could we do these? Could we do this with a linked list? And better yet, a really more important question is, can I do this on a linked list without worsening my time complexity? Okay, show that the merge sort is stable if and only if the merge step is stable. Could we improve the worst case, the best case, time complexity? How would we do it? And a better question is, would it be worth it? The answer is usually no. Because if I know that my data is almost sorted, I wouldn't use merge sort. If I know my data is almost sorted, I would use something like bubble or insertion, preferably insertion. But if I know that my data is not almost sorted, then that's when we use a more advanced sort. Okay, so that's done for today, exactly on time. And I'll get the review slides, I'll get those, finish editing those and post those, and I'll see you in office hours. Oh, also, one other thing I wanted to mention is for students that are in other countries that have issues with internet access, Gradescope, Canvas, and the AutoGrader all tend to be fine. I know some students sometimes have trouble with YouTube. If you look on Canvas, there's a region called the Media Gallery. So I took all of our lectures so far and uploaded them to Canvas Media Gallery, and I'm going to go do the same thing in a few minutes with today's lecture and get that posted. It'll take a little while to appear just because I've got to download from YouTube, upload to Media Gallery, and then it takes a little while to make it visible. So I'll get that done now. All right, I'll see people in office hours. Hopefully not everyone. Hopefully most of you are done with the project now.